Hello, I'm Jianjun Zhao from Kyushu University. Today I'd like to talk about some size and structure metrics for quantum software. This is the outline of my presentation. Software metrics aim to measure the inherent complexity of software systems to predict the overall project cost and evaluate the quality and effectiveness of the design. Software metrics has many applications in software engineering tasks, such as testing, maintenance, re-engineering, reuse, and project management. Research for software measurement must adapt to the emergence of new software development methods, and metrics for new language and design paradigms must be defined based on models related to these new paradigms. Quantum programming is the process of design and building executable quantum computer programs to achieve a particular computing result. A number of quantum programming approaches are available now, for example, Scaffold, Qiskit, Q-Sharp, Project Q, and Cooper. As research in quantum programming reaches maturity with a number of active research and practical projects, software metrics researchers need to focus on this new paradigm to evaluate in a rigorous and quantitative fashion. However, although a large number of software metrics has been proposed for classical software, few metrics has been proposed for quantum software. Further, due to quantum software's specific features, existing models and abstractions for classical software cannot be applied to model quantum software straightforwardly. As the first step towards evaluating quantum software, in this paper, we propose some basic metrics for quantum software which mainly focus on measuring the size and structure of a quantum software. These metrics are defined at different abstraction levels to represent various size and structure features in quantum software explicitly. The proposed metrics can be used to evaluate quantum software from various viewpoints. Especially in this research work, we want to examine: can classical size and structure metrics be applied to quantum software? And how can classifying size and structure metrics be applied or extended to quantum software? Next, I'd like to briefly introduce some size metrics for quantum software. Software size represents one of the most significant internal attributes of a software product. Therefore, many software effort estimation models use size metrics as their main effort driver to estimate the software development effort. Here, we introduce some basic size metrics that can be used to measure the size of quantum software from the level of code, design, and specification. Program code is an integral component of the software. Such code includes source code, intermediate code, and even executable code. Examples of classical code size metrics include lines of code, house-state software size. Here, we only focus on the source code of quantum software and discuss how some widely used size metrics for classical software can be extended to measure the size of quantum software. As we know, the most commonly used metrics of source code program length is the number of lines of code. The lines of code metrics can be used to predict the amount of effort required to develop a program, and can also be used to estimate the programming productivity or maintainability after the software product is completed. Similarly, for quantum software, we may also consider some lines of code metrics to measure the internal attributes of the software, especially related to the quantum attributes. Let Q be a quantum program. Some basic lines of code metrics for a quantum program can be defined like this. Here, as we observed, phi1 is a general matrix which consists of both classical and quantum statements that can be used to measure the total size of quantum program. We can also determine some metrics to especially measure the size related to the quantum aspect in a quantum program. Moreover, we can even consider the number of qubits or gates used in a quantum program to obtain phi 5 and phi 6 size metrics. Halstead introduced some size metrics for classical software. According to Halstead, a computer program that implements an algorithm is considered to be a collection of tokens that can be divided into operators or operands. Halstead observes that software metrics should reflect how algorithms are implemented in different program languages and independent of the platform and language used. These metrics should be compatible statically from the source code of the program. Let B be a classical program, which is a collection of tokens classified as either operators nor operands. Then some basic numbers for these tokens in the program can be defined like these. Here, mu1 and mu2 count the number of unique operators and operands in the program, respectively, and n1 and n2 count the total occurrences of operators and operands in the program. Based on these numbers, some size metrics can be defined further to quantify various aspects of a classical program, like this. So these metrics can be used to measure the length of the program, the vocabulary of the program, the value of the program, or even the effort required to generate the program. Similarly, we can define some basic numbers in a quantum program that consists of both classical and quantum statements. For example, we can count the number of unique classical and quantum operators and also operands, and also the total occurrences of classical and quantum operators and operands. So based on these numbers, we can define some metrics for a quantum program by extending the classical Halstead matrix. For example, we can measure the length of a quantum program, the volume of a quantum program, and the difficulty of quantum program. In addition to some code size metrics for quantum software, we can also define some design size metrics for quantum software. As we know, quantum software design is a process to transform user requirements into a suitable form that can help the programmer in quantum software implementation or coding. As classical software design, A quantum software design may also involve two stages: architecture design and detail design. Like measuring the size of quantum software at the code level, we can measure the size of quantum software design at both architecture design level and detail design level. Architecture design defines a collection of quantum software components, their functions, and their interactions to establish a framework for developing a quantum software system. The software architecture of the system defines its high-level structure, reviewing its overall organization as a set of interacting components. A well-defined architecture allows an engineer to reason about system properties at a high level of abstraction. We can measure the size of quantum architecture design based on formal architecture specifications. Let S be the formal architecture specification of a quantum software architecture, which consists of a group of components and the connectors between components. Therefore, we can define some architectural size metrics like these. Here, gamma 1 and gamma 2 are general architecture size metrics that can be used to measure the total size of a quantum software architecture. While gamma 3, gamma 4, gamma 5 are metrics that specifically quantify the size of the quantum aspects from different viewpoints. We can finally derive a general size metric gamma 6 to quantify the total size of the quantum-related aspects. Detail design refines and expands the architecture design to describe the internals of a quantum software components. For example, the algorithms, processing logic, data structures, and data definitions. Recently, some research has been carried out for study design patterns for quantum systems. We can define some design size metrics for quantum systems based on these quantum design patterns. Let D be a design for a quantum system. We can define some concrete metrics for the detailed design sets of a quantum system like these. Here, delta 1 or delta 2 are general detailed design size metrics that can be used to measure the total size of a detailed quantum software design. And delta 3 and delta 4 are size metrics that are specific to quantify the quantum attributes in terms of quantum design patterns. The unified modeling language is a general-purpose, well-known modeling language in the field of classical software engineering. It provides a standard way to visualize the design of classical software development lifecycle. Recently, researchers present some extension of UML to model quantum software system. In addition to the classical elements in a classical UML, the quantum UML also contains elements related to the quantum aspect, such as quantum class, quantum variables, and also quantum operations. Similar to the classical UML, quantum UML can serve as a base for defining some size metrics for a quantum software system at the specification level. An example of some metrics which can be used to quantify the quantum aspect of a system can be defined like this. For example, here, 31 count the number of quantum classes or objects, and 35 count the number of all quantum methods. Next, I'd like to introduce some basic structural metrics for quantum software. Structural analysis of programs is an essential component of software development and software evaluation efforts. Software metrics try to consider the complexity of individual modules and the interactions between modules in a system and quantify such interactions. Many approaches in structural metrics has been proposed. Some good examples include McCabe's Cyclomatic complexity matrix and the information flow matrix proposed by Harry and Carfrow. Here we discuss how these classical software metrics can be extended to evaluate quantum software. Like a classical software, structural metrics for quantum software can be defined at both code and design levels. A well-known metric for measuring the complexity of a classical program's control structure is the Cyclomatic complexity matrix by McCabe. For a program P, the cyclomatic complexity matrix V of P is defined as the number of linearly independent paths through the control flow graph of P and can be computed as follows, where G is the CFG of P to be measured. N is the number of nodes of G, each representing a statement in P, and E is the number of edges of G, each representing the flow of control from one statement to another in P. Similarly, we can measure the complexity of a quantum program's control structure by defining an extended cyclomatic complexity matrix for quantum software. The definition of such a matrix can be based on the quantum control flow graph, which is an extension of the classical control flow graph to represent a quantum program. Let GQ be the quantum control flow graph of a quantum program Q to be measured. The cyclomatic complexity matrix V of Q can be defined as follows. Where NQ denote the number of nodes of GQ and EQ denote the number of edges of GQ. By this way, we can extend it classical cyclomatic complexity matrix to the domain of quantum software. Perhaps the most common design structure metrics are known as information flow metrics, which deal with the complexity of a system by observing the flow of information among system components or modules. Among these metrics, one well-known approach is Harry and Carfrow's information flow metric, which measures the total level of information flow between individual modules and the rest of a system. These metrics consider the complexity of a software module, which could be affected by the following two factors. The first factor is the complexity of the module's code itself, and the second factor is the complexity due to the module's connections to its environment. The effect of the first factor has been included through the line of code matrix. For the quantification of the second factor, Harry and Carfrow has defined two terms, phi in and phi out. The phi in of a module is the number of local flows into the module plus the number of data structures from which the module retrieves information. And the phi out of the module is the number of local flows from the module plus the number of data structure which module updates. Based on this concept, Henry and Carfro defined their information flow matrix value as the module length multiplied by the square of find in multiplied by find out, where lines is the number of program language statements in the module, and find in and f out are the find in and find out of the module respectively. Next, I'd like to introduce how to extend Henry and Carfro's matrix to the domain of quantum software. A quantum software system is usually composed of classical and quantum modules. These modules are not independent and therefore may have some interactions among them, which may lead to some information flows from one module to another. To measure the complexity of a quantum system by observing the flow of information among the system modules, we can extend Henry and Carfro's information flow matrix to the domain of quantum systems. Let MQ be a classical or quantum module of a quantum system. Length MQ be the number of quantum program language statements in MQ, and f in and f out be the find in and find out of MQ respectively. We can define the structure matrix based on the information flow to measure the complexity as a module of find in and find out in the program as follows. Through this way, we can extend it Henry and Carfro's information flow matrix to measure the information flow complexity of quantum system. This paper has proposed some basic metrics for quantum software, which mainly focus on measuring the size and the structure of quantum software. Some of these metrics are the extension of their classical counterparts, where the others are specially designed to codify the quantum features in quantum software. We are now implementing a matrix collection tools for quantum program language Qiskit to automatically derive the result of the proposed matrix from Qiskit programs. The next step for us is to perform some experiments and collect data for evaluation. We hope a primary evaluation of this matrix will be available soon. Thank you very much for listening.